Good afternoon, ladies and gentlemen. My name is Innawi Ahmed, and I would like to introduce Professor Evan Gordon. Professor Gordon obtained his PhD in February 2002 in the field of novel magnetic material for sensors application from the University of Leuven in Belgium. He started to work at EMEC in Belgium in 2003, where he is currently leading the photovoltaic and energy system activities, working on advanced crystalline wafer-based and tail-film solar cell and module technology, including perovskite-based tandem devices, and on the integration of photovoltaic in the energy system for the future. He is also part-time professor in digital photovoltaic at the Delft University of Technology in the Netherlands, and he is the editor-in-chief of the Elsevier's scientific journal Solar Energy Material and Solar Cell. Impact factor 7.3 is huge, so it's a very important journal. And by the way, I am as editorial board with him. Since January 2016, he is the coordinator of the joint program on photovoltaic of the European Energy Research Alliance, EERA, and a steering committee member of the European Technology and Innovation Platform Photovoltaic. So he's the expert in photovoltaic, and he's very well known in teaching in the European community for leading European project. He will talk about status of crystalline silicon photovoltaic technology. And I want to thank him very much for accepting to be with us. Time is not easy, but he accepted, and I would like to thank him on behalf of all members of the Virtual Learning University. So the floor is yours, the virtual floor.
Okay, thank you very much, Ahmed. So let me share my screen.
Yes.
Let's see if this works. Okay. Yeah, first of all, I would like to thank you, Ahmed, and the other people involved in the virtual university for giving me this opportunity. So it's always nice to be able to be part of such a nice initiative and to give a presentation. And I think even in this case, the last presentation of the 2 weeks, I believe. So it's really nice. So indeed, today, I will talk a bit more in detail about the status of crystalline silicon-based photovoltaic technology. But I will start first with a little bit of general introduction on what is now the state at the moment of the PV technology in the world. And let me see if I can go to the next slide. So what we see today, if we look around us, we see that we are finally slowly moving towards a sustainable energy future. So we see more and more wind energy and solar energy and so on, other renewable sources being installed worldwide. So we can say the clean energy transition is finally really happening, and that's really what we need to save the climate. But if we ask ourselves, why is it now really happening? Why is this transition actually happening at the moment? I would say one of the reasons is actually the economics, because the transition at the moment is really driven by the fact that we have seen in the last years very large cost reductions in renewable energy technologies such as wind and solar energy. So here I give the example of the so-called learning curve of solar PV modules, where we can see actually data for the last 45 years. Starting from 1976, when actually the cost of a PV module was typically around $100 to $200 per watt peak, all the way to today, where we actually see that the cost is like only $0.2 per watt peak. So in 45 years, we have actually decreased by a factor of 1,000 the cost of the PV modules. And something similar is, of course, going on for other technologies like wind technology. So basically, if that means that if we look at, for instance, utility scale photovoltaic, so that means the big solar factories, solar farms, so where you have very large amount of PV panels, if we look at the cost of the electricity that they are producing, it's really the cheapest electricity source that we have today. together with certain wind applications. And for instance, that was also shown by the International Energy Agency at the end of last year, when they had a new report out, and they really called solar energy the king of electricity. So it's really the cheapest electricity source that we have ever had. And that's of course why you see now that more and more photovoltaics are being installed worldwide. So this is a curve that shows actually until end of 2020, the cumulative amount of photovoltaic modules that were installed worldwide over the years. So we see, if you look at 2020, at the end of 2020, in total in the whole world, there was roughly 760 gigawatts of PV panels installed. And of these 760 gigawatts, around 140 gigawatt was really installed in that last year, 2020 alone. So this is a very large number. And if we extrapolate, we see that probably somewhere in the middle of next year, the middle of 2022, we will cross the limit of 1,000 gigawatts, so 1 terawatt of PV panels installed worldwide. And you see also over the last 10 years that the amount of PV that we are producing and installing each year is really almost exponentially increasing. So in 2012, it was the first year that the total amount of PV modules worldwide reached the threshold of 100 gigawatt. And so it took from 1976 until 2012 to reach the first 100 gigawatt of installed PV. But actually a few years later, from 2017, we started installing 100 gigawatt per year. So it's really ramping up extremely fast. And of course, that is now really driven by the fact that it's really a very cheap electricity source. So it really makes a lot of sense to start installing PV everywhere. Now, if you look, what is the technology behind all these PV panels? So there are different technologies in the market. And this graph shows actually, as a function of time, a little bit the distribution of different technologies. So you see here 2 colors of blue. This corresponds to crystalline silicon technology, whether it's based on monocrystalline wafers or multicrystalline wafers. And then you also have a little bit of green here. These are alternatives based on thin film materials that I will discuss later, and which are probably already discussed in some other talks before. And so we can say that at the end of 2020, 95% of the PV market was actually based on crystalline silicon technology, so which is actually the focus of my talk today. And around 5% are then alternatives, which we call thin film photovoltaics, which are based on different materials. So what are now these different materials for the thin film? So I have a few slides on that. So these non-silicon based photovoltaic panels, they are either typically based on cadmium telluride, which had a market of around 6 gigawatt last year. And in second place is the CIGS, the copper indium gallium deselenide technology, which was probably also discussed in the previous talk by Professor Enaoui. And these are the 2 main alternatives. There are other alternatives, but they really have a very small market share at the moment. So if you look at the cadmium telluride, we can basically say that the 6 gigawatt is produced mostly by one company. It's the company called First Solar. It's an American company. And they really have the technology leadership in this technology. So they have been able to make very large, so 2.5 square meter panels with 19% efficiency. So that is around 500 watts that one panel is giving. And these are very robust and stable PV panels. And they are now manufactured in quite large capacity. So they have a capacity of 8 gigawatts, and they are expanding to 16 gigawatt in the future. And what is typical for cadmium telluride is that it really has the lowest manufacturing cost per watt in the industry. So actually the cost is lower than, for instance, for crystalline silicon. The main downside that this technology has is twofold, I would say. They're using cadmium, which is a toxic material, so people are a bit skeptic about that. But the main downside is that they use tellurium, which is a very scarce material. So we will never be able to produce this material in the same quantities as, for instance, crystalline silicon because of the scarcity of the material. But you can reach very high efficiencies with this material, and it is at very low cost. So that's why it also has still a relevant market share. Then some other alternative thin film technologies. We have the CIGS that has been discussed in some previous talks. So that's a quite complicated material. You can reach high efficiencies, but upscaling is still a little bit difficult. So commercial modules still have relatively lower efficiency, but there are companies producing this, and the production is typically a few gigawatt per year. People have also investigated for a long time organic PV materials. There, the main downside is that the efficiencies that you can reach are still quite low, but the advantage would be that these can be very, very cheap materials. And then a last material, which is sort of a relatively new material of the last 5 or 10 years, is the perovskite material. So in the beginning of the 2 weeks of this virtual university, there was also a talk of Professor Nazaruddin, for instance, who talked about that. And I will also come back to this material at the end of my presentation, because it's a very promising material to combine also with crystalline silicon technology. But the rest of my talk will be about crystalline silicon photovoltaics. And if we look at the value chain of crystalline silicon photovoltaics, so it's photovoltaics based on the use of crystalline silicon, and we actually extract silicon typically from sand. So how can we go from sand to a silicon PV module? We can basically distinguish 5 steps in the value chain. We first have to make from the sand very pure polysilicon. Then this polysilicon is turned into big crystalline silicon blocks, which we call ingots. The ingots are wire sawn into individual wafers. The individual wafers are then processed into individual cells. And then these individual cells, they are interconnected and they are encapsulated into the final PV module. And in principle, we can distinguish 2 types of crystalline silicon, which we also saw in one of the previous slides, depending on the type of wafer. So if we have a monocrystalline silicon wafer where the wafer is one single crystal, then typically we can get the highest solar cell efficiencies. But we can also make multicrystalline silicon wafers. These are wafers which are a little bit cheaper to make, but then you actually have multiple crystalline orientations in the wafer, and the efficiencies that you then can reach at cell level are a little bit lower. If we now look at the cost structure today of monosilicon PV modules, so we see here a graph that shows you how the cost has really decreased a lot in the last years. But if we look here at the right-hand side inset, we see actually the cost structure of a typical PV module at the end of 2020, a monosilicon PV module. And it's interesting to see how the costs are distributed. So the cost is around $0.2 per watt peak. And how is this distributed? Well, around 30% of this cost comes directly from all the steps we need to do to make the crystalline silicon wafer itself. So that's quite a lot. So we always think silicon is an inexpensive material, but still 30% of the module cost is directly linked to the PV wafers that we are using in the module. Only 12% of the cost comes from the cell processing. So from the steps and the materials that we need to turn the wafer into a working solar cell. And then roughly 60% of the module cost really comes from the materials and the processes that we need to interconnect the cells and encapsulate them. So materials include the encapsulation material, but also the glass and so on. So it's interesting to see this breakdown of the cost structure, because this has evolved a lot over time. So until a few years ago, for instance, the cost of the cell processing was relatively much higher. But now it's dominated really by the module cost and the crystalline silicon cost. So this is the outline then of the rest of my presentation. So in the first 3 parts, I will give more details of this value chain. So looking at how the wafers are typically made and what are some of the things that are happening there in terms of research. Then we look at how the cells are typically processed, and then finally how the modules are made. Then in the 4th part, I will talk about the way forward. So what is now the long-term future for silicon photovoltaics? Well, we believe that we have to combine the silicon with another material, like for instance, the perovskites, to go to tandem devices. And then at the end, I will also say a few words about sustainability. So we are already producing worldwide a lot of PV modules, But basically, to save the planet, we will still need to produce much more in the future. And then we have to wonder, is this really feasible? Do we have enough materials? Is it sustainable to have such a large PV production? But so I will start with the first part in the value chain. That is how we can go from sand to crystalline silicon wafers. So the silicon that we need as the absorber layer of our solar cell basically comes from sand, as we know. And the first step is always to make so-called metallurgical grade silicon. So this is already pretty pure silicon that is extracted from the sand, but it's not pure enough yet for electronic applications such as solar cells. So typically what is done, this metallurgical grade silicon is further purified to make it electronic grade silicon, and it is typically done in the gas phase. So we actually make a very pure gas, like trichlorosilane in this case. And once we have this very pure gas, then we can make actually so-called polysilicon rods. And traditionally, this is done in the so-called Siemens process. So what we do is we use this very pure silicon-containing gas. We have a large reactor, which is at a high temperature of around 1200 degrees. And we actually grow polycrystalline silicon material. So we go from the gas phase to the solid phase, and we end up with a very pure polycrystalline silicon material. Now, one of the downsides of this is that this process actually requires a lot of electricity, a lot of energy. So typically you need around 100 kilowatt hours to make 1 kilogram of polysilicon. So already for many years, people are investigating alternatives like the fluidized bed reactor, where you can actually reduce the amount of energy you need, because this is a really energy intensive and therefore expensive step. But whatever method you use, and the Siemens reactor is still the standard method, you end up with a polysilicon material, typically in the rod form here. And then actually what we will do is we will break this rod into small chunks, because we have to remelt this silicon to form the ingots. So that is actually the next step. And I will here take the example of monocrystalline silicon, where we use the so-called Czochralski process. So basically, what we do is we take a very large crucible, which is typically made from quartz or graphite, and we fill, so that's a very large pot, you could say, and we fill it with all these polysilicon chunks. We put it in a very large furnace, we heat it up until temperatures above 1400 degrees, so that the silicon is really melting. And then to make a monocrystalline silicon ingot, we have to start from a small silicon seed crystal, so a small piece of monocrystalline silicon with very nice crystalline properties. We put it on top of the melt, and we slowly take it upwards. And what happens then, actually, this molten silicon is sort of attracted, also goes upwards, starts to cool down, and starts to crystallize and takes on the same crystalline structure as this silicon seed layer. So in this way, we can slowly pull a cylindrical ingot from this melt. So it looks a little bit almost like a magical process, but it works really well. It's a well-known process, but again, it's at very high temperatures. It takes a long time, so it's very energy intensive. And at the end, you end up with very large so-called ingots, so very large blocks of monocrystalline silicon. This is called the CZ pooling, the Czochralski pooling. Now, once we have this ingot, typically what is done, the top and the bottom and the sides of the ingot are removed, because they contain lots of impurities and they do not have controlled doping densities. So we actually use only the center part of the cylinder. And this center part will then be sliced into individual wafers. And that is typically done by diamond wire sawing. So basically, we have a very long wire, which is kilometers long. And the wire is coated with small nanocrystals of diamond that give an abrasive effect. And basically, these wires are simultaneously slicing through the whole length of the ingot, creating a lot of wafers, typically with a thickness of around 180 micrometer. Now, one downside of this process is that you create a lot of curve losses. What does it mean? So we make wafers of 180 micrometers thick, but there where the wire is actually slicing, you actually lose typically around 80 to 90 micrometer of silicon. So we have to make a lot of energy intensive steps to make this crystalline silicon. And then when we are actually going to slice the wafers, we actually lose again quite a lot of silicon. So also here, there is lots of room for improvement, and a lot of research is ongoing to reduce these curve losses. And then finally, okay, we have the individual wafers, which can then be further processed into cells and modules. So if we look now at this whole, all these steps, we can say that actually to make these silicon wafers, it is actually quite a complicated process with a lot of steps, and especially a lot of energy intensive and expensive processes. And that also explains why 30% today, at 30% of the cost of the PV module is from these wafers. So there is still lots of room for improvement and for cost reduction. But on top also, we have all these energy intensive processes. So actually making the wafers is also responsible for a big part of the energy payback time and the CO2 footprint of the modules that we are making. To give you an idea, the energy payback time for a silicon PV module at the moment is around 1 year. Of course, it depends on where you use it, but so it means that the amount of energy you needed to create the silicon PV module is generated again by the PV module after 1 year. And of course, you can use a PV module much longer, 20, 30 years. So you will produce much more energy than you needed to put in. But a lot of the energy that you need to make the module actually comes from making the wafers. So here we can now look at some of the trends that we see happening in silicon wafers for photovoltaics. These are curves that come from the ITR PV roadmap. So that's a yearly roadmap that is made by the industry that predicts what is going to happen for silicon photovoltaics in the next 10 years. And so far, I've mostly focused on monocrystalline silicon wafers. And the reasons for that is that although in the past, until a few years ago, most of the PV panels that were made were actually, or let's say 50% of them at least, were made based on multicrystalline silicon. This is the dark blue here. But we see that in 2021, the amount of multicrystalline silicon cells that are still being processed is actually below 20%. And it's foreseen that it will more or less disappear in the coming years. So basically, all the crystalline silicon PV modules in the future will actually be based on monocrystalline wafers, either P-type or N-type, because you can simply go to much higher efficiencies with monocrystalline silicon, and the cost difference to make monocrystalline silicon wafers is compared to multicrystalline silicon wafers is actually decreasing. So it's not that important anymore. And then something else, which is really in a way surprising to see, is that until a few years ago, for many years, we had one standard size of wafers for silicon photovoltaics, which was 156 millimeter by 156 millimeter square wafers. But now, since a few years, we see a lot of different sizes appearing, larger sizes. And actually, it's foreseen that in the future, the so-called M10 and M12 sizes will really dominate after 2025. And these are wafers, still square wafers, which have dimensions of 182 millimeters by 182, or even 210 by 210 millimeters. So we really go to much larger wafers. And the reason is that it's becoming feasible also from a cost point of view to make good quality larger wafers like this. And at the same time, if you have a larger wafer, of course, you will have more power output from that wafer. Something else we see is that until now, most of the cells that were made were based on P-type wafers. And P-type wafers, traditionally, for silicon, they are boron doped. But the whole industry in the last years has been switching from boron doped wafers to actually gallium doped wafers. And the reason to go to gallium doped wafers is that it really helps reducing so-called light induced degradation. So what is this? So in boron doped wafers, you typically have the effect that you have boron oxygen complexes. And in some cases, these boron oxygen complexes, they can lead to degradation after a few years of operation. So that means that actually the efficiency of your device is reducing because of the presence of the boron together with oxygen. It creates special types of defects. So if you actually replace the boron by gallium, then you don't have this effect anymore. And on top of that, people have become also very skilled in making gallium doped wafers, and it turns out that the gallium doped wafers also have higher minority carrier lifetimes than the boron doped wafers. And that means gallium doped wafers are probably also better suited to really go to high efficiency devices. And so now recently also some patents that were present that explained how to make gallium doped wafers, they expired. And now everybody can actually make gallium doped wafers without having to pay for it, let's say, because the patents have expired. And you see now that the whole industry is basically switching to gallium doped wafers. So that was the first step in the value chain, basically. So how the wafers are made and what type of wafers we use. So now we have individual wafers. We have to process them into individual solar cells. And here I will give you a little bit of the history of how this went. So until 5 years ago, I would say the main cell concept that was used in silicon photovoltaics was a so-called aluminium back surface field cell, which is shown here. So it's a relatively simple cell structure where you use a p-type silicon wafer, so it can be mono or multi, and you make at the front an N-type emitter. You texture the front surface so that you have better light incoupling. You have at the front a silicon nitride layer that gives the blue color to the solar cell, so that acts as an anti-reflection coating and a passivation layer. And then you have at the front, you have metallization. You have these fingers, typically consisting of silver. So it looks like this from the front. So you have very thin lines, which we call fingers, and they are connected by bus bars, which are a little bit bigger transversal metal lines. And then at the rear, the whole surface is covered by aluminium, which forms together with a silicon and silicon aluminium alloy that acts as a back surface field. So this feature, the aluminium at the rear side, gives its name to the cell type. It's called aluminium back surface field. Now, the reason that this was used massively in the industry is that it's a relatively simple cell structure to process. You don't need a lot of individual process steps. The process steps are listed here. It can be easily done at large scale in industry, and you can get quite good and high efficiencies with it. As is shown here in some data that comes from a company, Hanwha Q Cells, that was producing for many years crystalline silicon solar cells. So here you see average cell efficiencies from their production lines using this aluminium BSF cell concept. And they started in January 2010. They had an efficiency on average around 17%. And over the next years, by tuning and improving their process and perhaps having also better wafers, they could further increase the cell efficiency more or less linearly in time, reaching each year an extra 0.6% absolute in their production lines. But then at some point, they around 20% of efficiency, they started having problems. They couldn't further increase it. So the efficiency increase stagnated. And the reason for that is that you bump into the fundamental limitation of this quite simple cell structure. And the limitation is actually at the back. So at this aluminium BSF that gives its name to the device. Because if you look at the rear, the whole rear of the silicon is in direct contact with the metal, with the aluminium metal. And this leads to a lot of recombination losses at the rear of the device. And this does not really allow you to make devices with efficiency higher than 20%. And that is a problem because, of course, you want to further increase the efficiency. So that's why, since a year or 5, let's say, I would say that the PV industry has started making the switch from aluminium BSF cells to a new type of cell, which we call perk cells. And at the moment, basically, almost everybody is producing perk cells. PERK stands for passivated emitter and rear contact cell. And the cell structure is shown here. So this is the aluminium BSF cell structure. And we know the problem is here at the rear, we don't want the whole surface to be in direct contact with aluminium. So what is done in this new cell structure? We put this blue layer in between. This is a dielectric passivation layer. And we open the blue layer in certain locations because we still need to make contact holes. We need to have some contacts between the aluminium and the silicon. So in this device structure, you have 100% of the rear surface in direct contact with aluminium. In this cell structure, it's only a few percent of the rear silicon that is in direct contact with aluminium. The rest is really passivated with this dielectric layer that is in between the silicon and the aluminium. Of course, it's a little bit more complicated cell structure. So you actually need 2 extra steps compared to the standard cell. You need to deposit or grow in some way this dielectric. And then typically you have to use a laser to make openings in the dielectric to be able to contact it. But these 2 extra steps, they do not really add a lot to the costs. So actually this perk cell now can also be produced at really low cost, but it gives much higher efficiency potential, which is immediately seen here in this cell, in this curve again of Hanwha Q cells. So we saw the black dots, which is the aluminium BSF cell. So they could not reach more than 20% in production. So at some point in 2014, they switched to the blue dots. This is the perk cell. They call it Quantum. That's their name for their perk cell. And we see that by switching to the new cell concept, they could actually again increase more or less at the same rate per year, and going to much higher efficiencies. But of course, also this perk cell now, it's clear it has a much higher efficiency potential, but it will also be somehow limited. And the question is, how far can we go with this perk cell concept? And in fact, what we find out then is that the efficiency limitations, the main efficiency limitation of the new cell concept, the perk cell, is also limited by the rear surface recombination. So we have only a few percent, let's say 3-4% of the surface now in direct contact with aluminium, but this 3-4% is still the weakest spot, let's say, of the device. That's still where the main limitation comes from. And so if we look at now the potential for this the perk cell, so these are curves that I took from Fraunhofer ISE from the past. So we can say that in industry with aluminium BSF cells, it has been shown that we can reach around 20% cell production. With perk cells, and this is already happening a little bit today, we expect that in industry you can produce cells up to 24% probably. But then again, you are limited, and the limitation comes really again from the surface at the rear. So if we want to now go further, and because this is now the cell concept that is massively used in the industry today, so we have to think about what is the next cell concept that if we want to go even higher in efficiency. And then there are several ideas. So we have to solve this problem with the contacts being in direct contact with the cell. So this can be by going to so-called passivating contacts. And we also see that more and more people are thinking about switching from P-type wafers to N-type wafers. And ultimately, we might go to a cell concept where all the contacts are at the rear. So I will explain that in the coming slides. But first, just to give you an idea, the whole industry now more or less switched to the monocrystalline P-type perk cells. So this is shown here. This is data from PV Tech Research for the crystalline-silicon PV production in this year. We see that almost everything here in blue is those are the cells being produced by the industry is based on the P-type mono perk that I just explained. And so you have like 5-6% of other types of cells being produced. And what are those? Those are already N-type cells. I will explain the concepts in the next slide. So we already have a few early adopters in the industry that are starting to produce the cell of the future. And then in green, you also have some people who are still lagging behind a little bit and are still making P-type BSF. But because efficiencies are not high enough, this is completely dying out, basically. So as I mentioned, people are considering now to switch more and more to N-type wafers. And why is that? because N-type wafers, they have a few advantages if you really go to high efficiency devices over P-type. So first of all, there is also this absence of light-induced degradation. I mentioned it before. So if you have boron in your cell, your wafer, you can have boron-oxygen complexes, and this can lead to degradation. Now, this can also be solved by going to the gallium-doped P-type wafers. So we don't really only need to go to N-type to solve this. But on top of that, typically N-type silicon has much higher minority carrier lifetime, so longer diffusion lengths than P-type. And the main reason for that is that N-type is less sensitive to certain transition metal contaminants. And the presence of such contaminants become more and more important if you go to higher efficiency devices. So if you have a cell efficiency of 20% and you have a little bit, let's say, of iron in your cell, is not such a big problem. But if you have a cell efficiency of 24, 25%, then having the same amount of iron can really kill your device. So the higher the efficiency, the more sensitive you are to impurities. And we have to consider that we have large factories now that are producing many gigawatts per year. And you will always have some contamination. It's unavoidable. So people have to, of course, take care to avoid as much as possible contamination, but we also have to look for those processes and those cell structures and those type of wafers that are least sensitive to the contamination that we are anyway going to have if we want to reach the high efficiencies. So that's the main reason that people are switching in the high efficiency concepts to N-type wafers. So then the next step for these N-type wafers to go to higher efficiencies will be using so-called passivated contacts. And with passivated contacts, we mean we still need to have metal contacts, of course, but the metal should never anywhere, not even a few percent of the surface area, in direct contact with the silicon. So there are two main types of passivated contact devices that are being considered, being investigated, and even already being produced by a few companies. The first one is a so-called heterojunction cell. So here, why is it called heterojunction cell? Because you typically have an N-type crystalline silicon absorber, and you passivate it on both sides with amorphous silicon layer, with very thin amorphous silicon layers. And you also use the amorphous silicon to create a back surface field and an emitter. So basically, because you have the combination of crystalline silicon and amorphous silicon, we call it a heterojunction cell. So you have actually a sandwich of a crystalline silicon wafer between two layers at the top and the front of amorphous silicon. On top of the amorphous silicon, then you have typically transparent conductive oxides for conductivity reasons. And then you have the metal contacts at the front and the rear. And we indeed see that the metal is in this case nowhere in direct contact with the silicon, because you always have the TCO and the amorphous silicon layers in between. This is a concept that is already existing since the 1990s, originally developed by a company in Japan called Sanyo that is now part of Panasonic. And in fact, over the years, and especially the last years, very high efficiencies have been reached. So the record at the moment is by an Australian company, and it's 25.5%. So it's pretty high. And already rumors are out there that now people have reached 25.8. So you can reach really very high efficiencies with this kind of cell. And it's also actually still relatively simple to process. You only need 7 main steps. Basically, you have to texture the wafer. You have to deposit twice these amorphous silicon layers, first on the front and on the rear, then twice the TCO at the front and the rear. Then you do the screen printing, metallization, and you do some curing, and basically your cell is ready. And because you have this symmetric cell structure, it's also very well suited for very thin wafers, which is also an advantage. Then the second type of passivated contact cell that has attracted a lot of attention in the last 6-7 years is a so-called Topcon cell. And this is a device that was originally proposed by Fraunhofer ISE. You have different names for it, but in different flavors, let's say also, but it's always actually as follows. So you have basically at the rear of your wafer, you have a thin tunnel oxide for passivation. And on top of that, you have a doped polycrystalline silicon layer that gives you the back surface field. And then you have the metal. So again, here you see the surface of the silicon is not in direct contact with the silver at any place, because you always have the tunnel oxide and the polycrystalline silicon layer in between. And this is not only a passivated contact, but it's actually also a selective contact. So this type of contact will typically attract one type of charge carrier, for instance, the electrons, and it will repel the holes, or vice versa. Also here, over the years, very high efficiencies of around 26%, both on N-type and P-type wafers have actually been reached. And some companies are already producing it in their production lines, trying to produce it. And we can again go to the example of Hanwha Q cells. So we had the black dots, which is the aluminium BSF. We had the blue dots, which is the perk cell, where you see that indeed it stagnates again around 24%. And now they are starting to produce also these Topcon devices. And you can see that they can reach around 25% in production. So some first early adopters are already trying to really produce this in very large quantities. So this means that we probably estimate that by switching at some point to passivating contacts in the industry, we will be able to produce cells in very large quantities, around 25 to 25.5%. But again, there will be some limitations there, and the higher the efficiency, the more and more difficult it becomes to surpass the limitations. So then the ultimate cell concept is probably the so-called back junction back contact cells, which I will explain here. This actually is a so-called heterojunction interdigitated back contact device. This is actually the world record device of the moment in crystalline silicon. So it's again a heterojunction device. It means we use amorphous silicon layers to passivate the wafer. Typically it's an N-type wafer, but now all the metal contacts at the rear of the device. So at the front of the device, we have no metal contacts anymore. So we have no shadowing losses. But it means also that the emitter and the back surface field regions, they have to be both on the rear of the device. So we have here alternatively the P and the N-type part of the device, and also the P and the N-type metallization. So the advantage of this device is that you have less shadowing losses on the front, so you can really go to higher efficiencies. But the downside is that it is much more complicated to make, especially in industry, because you have to have ways of patterning this rear surface. So the Japanese company Kaneka, with whom I have worked together for many years, they have in 2017 used this device to achieve what is still the world record efficiency for a single junction crystalline silicon solar cell. So they reached an efficiency of 26.7 with very high voltage and very high current density. So this gives us a kind of crystalline silicon solar cell structure roadmap for the next 5 or 10 years perhaps, where we see that at the moment industry is producing perk cells, and when all the companies are going to go to this 24%, they will probably switch to passivating contacts, and then ultimately they can switch to the back junction back contact cells, and they will be able to reach around 26, perhaps 26.5% in production. Of course, the physical limitations that you then still have are becoming very, very difficult to surpass. And actually, as I will show in a later part of my presentation, we will really have to go to completely new concepts if we want to even go higher than these 26 or 26.7%. We will have to go to tandem devices. So that was actually a little bit about what's happening in the world of silicon solar cell processing. But once we have the silicon solar cells, it's of course not finished. We still have to interconnect them and laminate them so that they actually form the module, which is basically the product that you can put on your roof or you can put in a PV power plant. So here, for many years, basically variations of the same standard process have been used, and I will actually explain this standard process. So if you look back again to a standard silicon solar cell, for instance, a perk type cell, typically how it looks is at the front, you have this H pattern. So you have these silver fingers, which are connected by broader bus bars, and you have an anti-reflection coating. If you look at the rear of the device, it is typically covered completely by aluminium, but you will also have some silver bus bars on top of the aluminium for solderability. So this is an individual cell, and now we have to interconnect individual cells together to a string of cells. And how is this done? Well, typically cells are interconnected using so-called ribbons, which are actually soldered on top of the bus bars. And so this ribbon that we use basically is made from copper, and the copper is coated with some coating that makes it solderable. And typically it's a few millimeters wide and a few hundred micrometers thick. And now what is done, and this is of course done in an automated way, these ribbons are placed on top of the first cell, soldered, and then actually the bottom part of the next cell is connected with the same string. So basically we always connect the top of the first cell to the bottom of the next cell, then the top of that cell again to the bottom of the next cell, and so on. And in this way, typically a string of at least 10 cells is actually interconnected. So these are 10 cells which are in series connected via these soldered ribbons. And so we make a lot of these strings, and these strings together will actually form the module. So the strings are typically flipped upside down, and they are placed on top of a encapsulation sheet, which is typically EVA in the standard process, which is placed on top of the cover glass. So this is the glass that you will see at the front of the solar cell. It's typically 3 millimeters thick, so that it can withstand, let's say, hail, for instance. And we, in the standard 60 cell module, we will place 6 of these 10 cell strings on top of such a glass. And then actually these strings, they're also connected together. This is called busing with large copper tabs. So basically, once you have done this, you have actually one large series connection of 60 cells. So you have 60 cells and they're all in series connected with each other. And of course, the cells are sorted so that all of these cells, they more or less have the same current density, so that when you connect them in series, you don't have extra losses. And then finally, you put another sheet of encapsulant, typically EVA, on top. You make sure, of course, that you can have your contacts outside of that encapsulant. We put a back sheet to protect from any kind of moisture ingress. That's typically a combination of different materials. An aluminium frame is put around the module, and you typically put the junction box with the output cables and some bypass diodes. And then basically you have made your module in this way. And this is, we call it a standard process, has been used for many years, and it's really robust, so it doesn't lead to a lot of degradation in the field. Of course, there are variations on this process. You have to do also other types of interconnection if you have, for instance, the back contact solar cells. But I will not go into those details here. This is still a process that is let's say, the basis of many of the module producers. So what we have seen now over the years is that by, of course, improving the cell technology, the wafers and the module technology, slowly also the output of such a standard module has increased. But especially in the last years, if you look here from 2019, we see a very fast increase in the output power of the module. So before, for many years, we went from 300 watts for one module to 400 watt by slowly improving the cells and so on. Now we see all of a sudden that Yeah, lots of companies are bringing 500, 600, even now close to 700 watt modules on the market. Typically, this is because people are switching to larger cells, but also to larger modules. So instead of 60 cell module, you can make a 72 or an 84 module. And so, but it's going very fast, the increased output of the modules. Some other trends that we see is that traditionally, the PV modules that were made were all more or less very similar because they were all used for the same applications, you know, residential applications where you put the PV panels on your roof, or let's say utility scale power plants where you have just a very big power plant with many of these modules put together. But in the last years, we see that there are many new applications that are becoming very prominent. So for instance, building integrated photovoltaics, where you don't simply put the PV on the top of a building, but it can, for instance, be part of the facade of the building. We see also for electric cars that there is more and more interest in also integrating PV on the electric cars. You can put PV on roads, in sound barriers along the roads, for instance. There is floating photovoltaics more and more, so where you put actually the PV modules on water, even on the sea in some cases. There is agri-photovoltaics, where you combine actually photovoltaics with agriculture. So you use actually, for instance, in some type of greenhouses. So we have more and more of these applications, and all these different applications, they require actually different specific types of modules. So you have to really tune the module to the application. And of course, in some of these applications, it might also be that perhaps crystalline silicon is not the best material, but one of the thin film alternatives could be a good solution there. And then what we also see is that there is again more and more distributed, and that means local production. So companies are investing in actually producing the PV modules really close to where they are going to sell it. And one of the reasons for that is also that actually the shipping cost is becoming non-negligible, because the cost of the PV modules is becoming so low. Actually, the shipping cost is becoming quite substantial. And especially nowadays in the COVID times, and we see that there is many problems also worldwide in delays in shipping and so on. So that's another reason why it's really interesting to again locally start producing the modules and perhaps also the cells. And then finally, what is also becoming more and more important, especially in Europe, is so-called eco-design. So that we actually are going to see not just how we are going to make the cells and the modules to have a higher efficiency, but also how we can make them to have a lower CO2 output during the production, how we can use, for instance, already recycled material in the modules, but especially how we can actually design the modules so that they can be much easier recycled and perhaps reused also in some cases. So that was then basically going through the whole value chain. We have seen how we now start from sand and we end up with the silicon PV module. Now I want to have a look a little bit further in the future and look at what is now the future for silicon photovoltaics. And it will be based on silicon tandems. So I've shown you that the world record cell efficiency for silicon is 26.7%. Now, if we look, the theoretical efficiency limit of a single junction silicon solar cell that has been calculated in the past in different ways, it's around 29.4%. So that's a relatively low number, you could say. And why is that? Because of the spectral mismatch. So a lot of the energy that is in the incoming light from the sun is actually not really used in a single junction silicon solar cell, because there is a lot of light that has too low energy to cross the band gap, so that is not absorbed. But even the light that is absorbed, a lot of the energy is lost in terms of thermalization. So that's actually what we see. We will never be able to go above 29.4%. And of course, in practice, it will be very difficult to reach the theoretical limit. So the practical limit will rather be around 27% probably. So if we go to this roadmap that I showed you before, what does it mean for silicon? We know we have more or less a way that we can reach 26, perhaps even 27%. but then it will stop because we have this theoretical barrier that we cannot cross. So will this be the end of silicon solar cell technology evolution? Well, no, because we will be able to surpass this limit if we go to so-called multi-junctions, where we actually put different materials with a different band gap on top of each other. This is not a new concept that already exists. For instance, for 3.5 space applications, they make very expensive triple junction solar cells that can reach efficiencies above 40%. But we will now try to do something similar using crystalline silicon. And so the idea is, if instead of having a single absorber, we actually take the crystalline silicon as a bottom cell, but we put a high band gap thin film top cell on top, we will actually be able to use more energy from the spectrum that is incoming. So the top cell will mostly work with the high energy photons, and then the bottom cell will work with the low energy photons. And if you then do the theoretical calculations, you see that for a double junction like that, the theoretical efficiency limit is above 40%, even up to 44%. And the good news, so this is a plot where you see the maximum efficiency that you could reach as a function of the bottom cell band gap and the top cell band gap. And the good news is that the highest efficiency region is when your bottom cell is between 0.9 to 1.1 EV. And 1.1 EV, that's actually the band gap of silicon. So silicon is really a good material to achieve a high efficiency. So we can use silicon with a band gap of 1.1 as the bottom cell. Of course, there are also other materials like CIGS could be used. And then we see that the top cell should have a band gap of around 1.6 to 1.7 EV. And there the perovskites, which I will explain now in the coming slides, are actually a very good candidate. But of course, also 3.5 or even certain chalcogenides could be used. So I will not go in too much detail in the perovskite materials, because I think there were already other talks, like the talk of Professor Nazaruddin in the beginning of these 2 weeks, that went into that. But the organometallic halide perovskites, they are kind of a new material that in the last 10 years has attracted a lot of attention in photovoltaics. So they have this crystal structure, which is the perovskite crystal structure. And it's sort of a combination of organic and inorganic elements that you put together. And the advantages of these materials are that you can simply fabricate them, so they are quite inexpensive. You also only need a few 100 nanometers, and they have a tunable band gap. So you see, you can really tune the band gap, and that's good because we need a band gap for the top cell of around 1.7 EV. And especially why they have attracted so much attention is that you can really, in a single junction on their own, you can really reach very high efficiency. So the record at the moment is 25.5%. So this is already very close to the maximum efficiency of silicon even. But of course, it's still a relatively new material. So all these cell efficiencies, they are typically on very small areas. And if you go to higher areas, then the efficiency is still a lot lower. So there is still a lot of research needed to in the coming years to make this a better material, let's say, for photovoltaics, but it has a lot of potential. And so the idea is that then we want to combine these perovskite materials together with silicon to make a tandem device. And then there are 3 different possibilities that are being investigated, depending on how you do that. And we can classify them according to the amount of terminals that they have. What does it mean? It means how many metal contacts will these devices have. So the first version is the 2-terminal device. So that means you have 2 cells on top of each other, but you still have only 2 contacts, like in a regular silicon solar cell, for instance. So this is called a monolithic device. And the main advantage is that it's a simple interconnection. It's as if you can just replace the standard single junction cells with this double cell. But the challenge here is that you have to grow the top cell on top of the bottom cell. So that's not straightforward. I mean, without, of course, limiting the efficiencies of both devices. And also this device is series connected, so both cells are in series. So it means you also need current matching, which is also not so easy to achieve. So the second possibility that is being investigated is then going to a so-called 4-terminal device. So in a 4-terminal device, as the name suggests, you actually have 4 contacts, 2 from each of the devices. So this is called also a mechanically stacked device. And basically what you do here is you develop the 2 cells separate from each other, and then you just connect them together with some optical coupling layer. So the advantage here is that you can independently fabricate these cells. They don't tamper with each other. And you also they are not in series, so they are operating independent from each other, so you don't need to have any current matching. So that's much better for when you have spectral variations during the day or during the seasons, for instance. But you have 4 terminals, so that makes the exterior electronics a lot more complicated. And you have this optical coupling layer, you have more layers in the top cell and the bottom cell, so you might have more parasitic absorption losses. These are the 2 main routes that are being investigated. But there is also something in between these 2 called the 3-terminal device, which is still a monolithic device. So you grow the top cell on top of the bottom cell, but you have actually a 3rd terminal here in the bottom cell, which allows you to bypass the current matching. So in this case, you don't need current matching. The idea of the 3-terminal device is that you try to have the best of these 2 combined. But the challenge is that you might also end up with problems of the 2 combined. But these are the 3 device structures that are typically being investigated. And if we then see for perovskite on silicon tandems, also in the last years, a lot of people have started investigating this, including even companies. And at the moment, the world record efficiencies achieved for perovskite on silicon are 29.5% for the 2-terminal, done by the company Oxford PV, and 29.2% by TNO in the Netherlands. And that's for a 4-terminal device. And in both cases, we indeed see, well, at least in this case, we indeed see this efficiency is already above the theoretical limit of crystalline silicon. So this will really be our way forward to reach efficiencies in the end for silicon PV modules produced by industry above 30%. For now, all these results are still on small area, so there is still a lot of work to be done in the next 5 to 10 years to upscale this and make this really a reliable technology with efficiencies above 30%. But so in general, I think the whole crystalline silicon PV community agrees that this is really the way forward. And by switching to the tandem cells, let's say in 5 to 10 years from now, we will be able to further increase also beyond the limits of the silicon technology. Then I want to finish with a few slides on sustainability. So we know that actually in the future, we will still need to produce and install much more PV than what we do today. So the question is that sustainable? And is that sustainable to do that with crystalline silicon? So there has been a recent paper out by Fraunhofer ISE, the link is here, where they have investigated this. So first of all, we have to think how much PV modules will need to be produced in the future. And of course, yeah, we don't have a crystal ball, so we don't know exactly. It really depends on the type of scenario that you look at. So in this paper, they looked at 2 scenarios. Scenario 1 is more a conservative scenario. Scenario 2 is more an optimistic scenario. But what we know in general is that if you want to be climate neutral by 2050, then we have to electrify almost all energy. And then at least 50% of electricity should be generated by photovoltaics. So this is for sure a given. But if it is 50% or 60 or 70, yeah, we still need to see. But here you have some ballpark figure numbers. So if we want to go for the climate neutrality, and we look at these 2 scenarios, then we know that by 2050, we need to install around 20 to 80 terawatt of photovoltaics, and this even increase further to 80 to 170 in 2100. what does it mean? As I mentioned in one of the first slides, probably next year we will have 1 terawatt of installed photovoltaics, but in 2050 we will need at least 20 and potentially even much more than that. So we still have a long way to go. So if you now translate these figures into how much extra PV modules do we need to install year by year, then you get these values. So after 2030, in 10 years from now, we have to install around 1 to 2 terawatt per year. So a terawatt is 1,000 gigawatts. So today we are producing and installing around 200 gigawatts. So it means in 10 years from now, we have to produce 10 times as much as what we are producing today. And of course, in the future, even we have to produce more. So these are the numbers we can work with. So is it now feasible for us to produce in 2030, let's say 2,000 gigawatts of PV modules based on crystalline silicon per year? Well, the conclusions of this paper, and they looked at some things like the energy demand, the glass demand, the silver consumption for crystalline silicon. The conclusion is that it is actually feasible to do that in a sustainable way, but not with the technology as we have it today. Because if we would say, okay, PV electricity is the cheapest electricity today, so we have the technology, we don't have to do anything anymore, we just have to produce it now in larger quantities, then we will not make it in a sustainable way. So we need further technological learning. For instance, if you look at the energy amount, the energy consumption that we need, I showed you already that you need a lot of energy consumption, for instance, to make the wafers. We have to continue to further improve the technology so that we can produce with less electricity need, because otherwise the energy demand will become really higher than let's say here 10% of the global primary energy consumption. So that is not acceptable. So, but if we can stay on the same learning curves that we have today, that means the technology is further advancing more or less at the same pace as what we have today, then we can probably limit this to 2 to 5%, which is still quite substantial, I would say. So it means that many years from now in the future, we are producing PV panels to such an amount that the energy we need for this production is 2 to 5% of the total energy that we are consuming. So it's still a high number. The same thing for glass. All PV panels have at least one glass at the front, but in silicon now, more and more, you have also a glass at the rear. So also the glass demand will become very high unless we can use thinner glass, for instance. But still in the predictions here, it might be that we have to ramp up a little bit the glass production worldwide just to be able to accommodate actually the PV production. We use silver typically for metal contacts in silicon photovoltaics. Also there, if we would just keep the silver amount in the cells as it is today, we would actually very quickly exceed all the silver mining that we have today. But if we can keep on progressing with the technology at the same rate as we have been doing in the last 10 years, then we can probably keep the silver consumption more or less at the current levels. So the conclusion here is basically it is feasible to have the necessary amount of PV panels based on silicon that we need in the future, but only if we further advance the technology. Otherwise, it will not be possible. So that brings me then to the conclusions of my talk. So we have seen that single junction crystalline silicon is getting close to its ultimate practical efficiency of, let's say, 27%. I walked you through the value chain from wafer, cell, and module. In all these steps in the value chain, there is still lots of room for technology improvements. And this is not only needed to have further cost reductions and efficiency improvements, but actually also it will be needed for us to be able to have a sustainable large-scale deployment in the future. And finally, the whole sector really believes that the crystalline silicon-based tandem devices will be the way forward, let's say in 5 to 10 years from now, to be able to produce efficiencies above 30% at low enough cost. And with that, I would like to acknowledge some colleagues from different institutes that helped with these slides. And of course, I would like to thank you also for your attention.
So thank you very much, Professor Ivan Gordon. It's a very good overview which show exactly where we have to put the manpower, where we have to work hard to make things clear, and this thing with the sustainability, it's really new for me. I also thought that we have already the technology, we have just to scale up, but it turned out that we will have some difficulty if we go to terawatt and so on. Is it? So
yes. So when I saw this, I also thought it's good news in a way, because it means there will still be lots of work for us in the future.
Yeah.
So
for researcher, yes, and for the next generation of researcher. So thank you very much. It's really, for me, it's a very, very important conference, because there are many points where one can think about it for the young researcher to go forward and especially to this thing to go to delocalize the industry in countries where the price can be low regarding the transport and so on. So I will give the floor to Salem, Ustad Salem, to make things running for the audience.
Thank you, Professor Ahmed, and thank you, Professor Ivan. It was interesting, really. You send us to the future foresight for the technology and the possibilities which is there, and this is good, optimistic, and it gave us motivation for more research. So let's see if there is any questions or any comments from the participants. All of you, it is allowed. You can raise your hand, or you can write your question in the chat. You have a few seconds. Who wants to ask or to comment? All right, so starting with Professor Ahmed.
Yes, I have one question, which is, for me, I would like to understand the basis. If you have high efficiency solar cell, it became very sensitive to impurities. How do you explain this? Is because the level in the band gap are more sensitive for recombination? What is exactly the
yeah, well, yes, it's really all about recombination. And of course, if you have the same amount of impurities and the same type of impurity in different devices, they will have more or less the same effect, independent of the device structure. But if you have a cell where you have only 20%, for instance, the aluminium BSF, you will have much more recombination basically at the surface of the device, which sort of hides that you also have recombination in the wafer itself, let's say. So what I wanted to say with that was basically the higher your efficiency, the better you have been in excluding all kinds of recombination and losses. And then the remaining losses, they become more and more important, basically. They're always there, but they become more important because all the other losses are gone and they are not hiding it anymore. So it's basically, Stefan Glunz always uses this this comparison with the leaky. With the leak.
Just a minute. Who's there? Please close.
Yeah, it's okay now, I think. So Stefan Glunz always compares this with a leaky bucket. So imagine you have a bucket of water and there are holes in this bucket. So if you pour water, the water will go through the holes. If you have a big hole at the bottom of the water, this will be the dominating hole. If you plug this hole, there will no water coming through that hole anymore. But then you have smaller holes on top of the bucket, which start leaking more. And this is actually the effect that I was mentioning. So the metal contamination is always there. It leads to small leakage, but you don't notice this leakage that much if you have a low efficiency. It's only when you have higher efficiency, because you have solved the bigger problems, that you see these smaller problems.
Okay.
And you have to overcome them then, because otherwise you cannot push your efficiency higher.
Okay, thank you very much.
Yes. Any other questions, comments from Abdul Samad? Thank you very much, Gordon. It was an excellent presentation summarizing the solar energy cells technologies. We have, yes, Professor Abdul Ilah. You can start, Professor Abdul Ilah.
Thank you very much for this nice talk. And for the tandem with organic inorganic perovskite, what about the stability of this of the organic inorganic perovskite?
Yes. So yeah, I think there are other people like Professor Nazuruddin that can answer that better, and perhaps they would discuss it also in his talk. But indeed, the perovskite material is a very promising material, but there is still lots of need for research there. There are two main issues. There is the upscaling to large areas and retaining the high efficiency, but there is indeed also the stability, which seems to be, yeah, at the moment for some of the devices problematic. Now you have already companies like Oxford PV. They are planning to actually start producing tandem devices in the near future. So they say that they can actually produce these materials and make them quite stable. So in my opinion, it's not 100% clear yet whether we will be able to solve this stability problem, but I'm quite confident because these perovskite materials, they are very versatile. So you have many different options, actually, many different knobs that you can turn, and together with the right encapsulation materials, it should be possible to make these materials stable enough. The same thing has been done over the years for the organic materials. So you need to find the right type of perovskites, so to get the intrinsic stability, and then in combination with the right encapsulation processes and materials, which should of course not be too expensive, because then again it will not be good. But if you can find the right material with the right internal stability and then combine it with the right encapsulation, there is a good chance that you can make it stable. Of course, the silicon PV industry will never switch to a tandem device if they are not sure that the top cell is stable enough. So we are all hoping that perovskite, because it seems to be the best material from cost point of view and from potential point of view, we hope that we can make it stable, but there is still lots of work needed in the coming decade to do that. If it turns out that we cannot make perovskite stable enough, then we'll have to look for another type of top cell. Some people are also working on 3-5 materials. Typically, we think, okay, 3-5 materials might be too expensive, but you never know what. We know for sure that 3-5 materials are stable. So you never know what the next years will give in terms of technology development that perhaps make those materials cheap enough. So it's not 100% guaranteed yet that the tandems will be based on perovskite. We need to solve some issues like stability for that. But it is clear we have to find a good top cell material, because we have to switch at some point the silicon technology towards tandem technology.
Thank you very much for this nice answer. Thank you very much.
Thank you. Right. Any others?
I think there is a question in the chat.
Let me go. Yes, you can read it there.
So do you guess that the materials available for building future energy by solar cells that could cover the world needs, gallium and others? Yeah, so this is part of the last slides that I showed you. In this study, we we, for instance, the study that I showed from Fraunhofer-ISE, they look only at a limited amount of elements. But indeed, for instance, if you think about the heterojunction cells that I showed you, you need a transparent conductive oxide. Many people in the past always use indium tin oxide, for instance, but there is indeed also not enough indium. So that means the sustainability question is only at the beginning. It's only in the infancy, I would say. So we really have to investigate very carefully also other elements. And for instance, if we need TCOs in the future devices, for instance, in tandem devices, people are also thinking of combining a heterojunction with a perovskite. So then you probably need some TCOs. They should really be TCOs that consist only of abundant enough materials. So the sustainability question is a question that will pop up more and more and will define basically the direction in which the research will go. So it will not only be longer about reducing the cost further and increasing the efficiency, it will be more and more about changing the technology so that we can sustainably produce it in large enough quantities to cover the world needs. So that's where I think the direction of research is going to. So it's not, I mean, yeah, we just have to find ways to sustainably produce, and that is the main thing that will dictate what topics will be researched in the future.
Thank you to Abdul Samad for your question. I think no other questions there. So we reached to the end of these opening sessions. So thank you to all. I will just want a conclusion from your side. Then Professor Ahmed, he will end related to all these sessions that we had it from 16th of October. Yes, Professor Ivan Gordon, we are happy with you within the last or the ending lecture. Please, your comments.
Well, yeah, it was a real pleasure and an honor to be invited here, and especially to give the last presentation. So, so yeah, I'm looking forward to hearing more about this initiative, and I'm definitely also willing to be part of it in the future also, if I can help in any way. So I think it's really a great initiative, and yeah, we need more initiatives like this. I mean, we really have to spread the news, the word, I would say, that, you know, we have the possibility to do good things for the climate, but it will still take a lot of action and research, especially, and we have to really involve the whole world into this. We have to work together. That's the only way that we can succeed in this big challenge, I would say, concerning climate.
Thank you. Thanks. We hope to see you soon, inshallah. We are all together within VLU. So, Professor Ahmed, ending.
So, first of all, thank you, Ivan, for this nice talk and a lot of points which are known, but we don't know it enough. And today, it's a lot of things are crystal clear for me, at least, and I think for the whole community. And I think the virtual learning university is open for you every time. And I hope we will invite you many times for webinar and so on. And also maybe you can organize a virtually lab tour in your lab that we can see it on our, for all people. In the future, I'm sure it will be a lot of people interested, since we are now in the beginning. I think we had a very good talks during this 2 weeks. Is from every aspect of from solar cell to water desalination to the climate change and so on. And I think it covers a lot of topics, and we will look for other topics which are missing maybe. And I think we will continue with this initiative. The syllabus, what some colleagues have offered to us, and they are willing to give course, we will show everything on the web page of the conference of the virtual learning university, when a syllabus will start, and etc. So if you stay tuned, you can see all the information, and also we will inform you via social media about our activities. So from here I want to thank all speakers from these 2 weeks. I can't give all names, but we will have all presentation on our web page. We will have video on worldwide. It will be broadcasted. So and we will stay in touch with everyone, with every speaker abroad, or our speaker which are also member of the university. So thank you very much. Thank you for the audience. Stay tuned with us. Then you will get more information. Thank you, Evan, again for your presence, for accepting to be with us. I think the solar energy material in solar cell is a journal which accept very good research, very good topic, and maybe we will put it on our web page of the virtual learning university, if you allow us to do this, that people can see they can go in and see what is the topic of solar energy material and solar cell, and the scope and so on. Thank you very much for everyone. Thank you, Ustad Salim, for being with me the whole 2 weeks, and also for audience. They are always there. Some of them, they are always there. And thank you, Professor Ben Youssef, for being member of the virtual university and for being always with us. And I wish you a good weekend and best wish for all of you.
Thank you. Bye-bye.
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 Bye-bye.